Okay, good day everyone. So today we will begin with our chapter 4 for KJM 442 heat and fluid. So in chapter 4 the topics uh, to be covered are refrigeration and air conditioning. So I've divided this into two different parts. So part 1 we will cover the topic focusing only on refrigeration, and air conditioning will be covered in part 2, which will be the subsequent presentation after this. So as mentioned, chapter 4 we have refrigeration and air conditioning. So in this presentation we will cover refrigeration. So that is our part 1. Right. So in chapter 4, refrigeration and air conditioning, we have these are the subtopics. So subtopic number 1 is on reverse Carnot cycle and coefficient of performance. So you will need to know what is a reverse Carnot cycle and what do you mean by coefficient of performance. You will also be exposed to heat pump, and this is followed by practical refrigeration cycles based on pressure enthalpy diagrams for refrigeration cycles. And for point number 4, you need to know what are the properties of a commercial refrigerant. You'll be exposed to Dalton's law and Gibbs-Dalton's law of mixtures. And for 4.5, you will then be taught on what is a psychometric chart and how to use a psychometric chart to solve problems related to air conditioning. So there are a few objectives here that we need to cover. All right, so once you have finished this chapter, right, so you should be able to describe the concepts of refrigerator and heat pump. So as I've mentioned here, right, so we have refrigeration. So under refrigeration, right, you have refrigerator and heat pump. So you should be able to differentiate between the two, and you should be able to measure their performance. Second objective is you should be able to analyze the ideal compression refrigeration cycle. You should be able to analyze the actual vapor compression refrigeration cycle, and as you can see, both are different. Although they are referring to the same refrigeration cycle, we will see that there are some differences between the two. uh, then we have this another objective on how to use the psychometric chart as a tool to determine the properties of atmospheric air. So these are the objectives that you need to know in order to what you call that master this chapter 4 under refrigeration and air conditioning. So let's begin with our introduction. I'm sure you are familiar with refrigeration. All of us, we've got a refrigerator at home. So do you know how it works? What is the function of a refrigerator at home? So if you look at the diagram that is shown here, what we have is we have a carton of milk, and this milk must be kept cold if you want to preserve it for a longer period of time. So what the refrigerator does is it takes away the heat from the milk carton and then make sure that it is kept in a cold environment so that you can preserve the content of this milk carton, which is the milk itself, so that you can use it for a longer period of time. If you leave this milk outside in the outdoor environment, this milk will spoil within a few hours or within a day. So in order to increase the shelf life of this milk, we will need to refrigerate it, and that's where the refrigerators in our house comes in. Imagine your life today without refrigerator. So let's do some history on the refrigeration. So the earliest and most common of the cold substance used for taking away heat was ice and snow. So Malaysia, we don't get ice or snow, but in cold climate countries during winter they get a lot of ice or snow. In some countries like Iran, they used to collect snow during winter, and they used to keep them underground, and then they use it in the summer for food preservation. So the Chinese, Greeks, Romans, etc., they've all used ice for food preservation. Now, if you look at the definition here, refrigeration is nothing but a process of making something cold, and cold can be defined as an absence of heat. And why we need to make something cold? It's because we want to extend the shelf life of that particular food product. It is mainly used for food, uh, extending the shelf life of food products, but now we know that in industries refrigeration is used in many applications, which we will see in this chapter later on. Now this is an example of a refrigeration machine that was developed in the 1834. As you can see, it's a very crude machine. It used to run with the help of very big compressors like this. They were either run manually or they were powered by steam engines. And the basic components of a refrigeration cycle, as you can see, or refrigeration system consist of evaporator, where your refrigerant evaporates to absorb the heat, which goes through a valve, and then you have a condenser where you reject the heat into the environment, and the compressor is where the refrigerant is compressed to high pressure and also to high temperature. So this was the refrigeration machine they used in 1834. It was very big and mainly used in the industries or factories to produce ice, and then this ice in turn was used for food preservation. Then in the 1950s, we managed to shrink the compressor, but it was still a very big, bulky compressor. Again, this was run either by a steam engine, or by that time we would have got electricity, and this was run by electrical motors or by electricity. So this compressor again was very bulky, and mainly it was the application of refrigeration was limited to industrial applications, where they were used to manufacture ice, and then that ice was then sold to uh, individuals for their domestic application. So again, the components here, as you can see, it consists of compressor, evaporator, you have an expansion valve, and also a condenser. So these were the refrigeration machine in the 50s. Then came the 60s, 70s, and 80s. We were able to shrink the compressor to a very small component, and then we started having refrigerators at home. And then this is what you see for refrigeration machines that you find at home. And what it does is the compressor actually delivers the refrigerant to the hot condenser coil, where the heat rejection takes place, and then this is returned via the expansion valve to the evaporator section in the refrigerator to absorb the heat from the confined space, and then this is the process and is then repeated again and again. As you can see, refrigerator is a very reliable piece of equipment. They hardly break down and they require almost zero maintenance. A refrigerator can last, if it's taken care properly, more than 10 to 15 years, and it is an essential device or essential machinery that we must have in each of our homes today. Now we will cover what is a refrigerator and what is a heat pump. Now we know from the science of heat transfer, the transfer of heat is only from the hot region to the cold region. You cannot have heat transfer from the cold region to the hot region. So, but in refrigerators, the transfer of heat is from a low temperature region to a high temperature region. So this is not natural. So in order to do this, if you want to transfer heat from a low temperature region to a high temperature region, you need a special device. And this special device is called refrigerator. Now the main purpose of a refrigeration, as you can see here, is to transfer heat from a chamber so that the temperature inside is reduced to below that of its surrounding. That is the main purpose. Now besides refrigerator, we have another device that transfers heat from a low temperature medium to a high temperature one, and we call that a heat pump. Basically, a refrigerator and a heat pump, they are the same thing, but they differ in their objectives, right? So you can see here, refrigerators and heat pumps are essentially the same devices, but they differ only in their objectives. As you can see in this diagram, figure 11.1, we have both the refrigerator and heat pump. So the refrigerator, the function of a refrigerator is to maintain a cold refrigerated space in a confined area, like a fridge. So you absorb the heat from this cold refrigerated space with the help of this refrigeration cycle, and then this heat is then rejected to the warm environment. You don't use the heat. Your objective here is to maintain the cold refrigerated space. Whereas in a heat pump, you have the same processes, but here the objective is different. We absorb the heat from the cold environment and we reject it to the confined space. For an example, in this case here we've got a house where we need to heat up the house because this house is experiencing cold weather in winter. So what you do is you absorb heat from the cold environment outside where it's snowing, absorb the heat from there, and then with the help of a heat pump you supply this heat so that you can warm a house during winter. So as you can see here, the devices are the same, but the objective of a refrigerator is to maintain a cold refrigerated space by rejecting heat into the warm environment. But for a heat pump is you absorb the heat from the cold environment and you maintain a warm refrigerated space. You can say that, right? So these are some of the important terms that you should know. And then we have this term called coefficient of performance. Coefficient of performance is nothing but the efficiency of the refrigeration cycle. Now, why we use coefficient of performance and not efficiency is because in a refrigeration cycle, your desired output can be more than your required input. As a result of that, your COP can be more than unity. So it can be more than one. So in order to avoid the confusion, so instead of using efficiency, we use the term coefficient of performance here. Now you have coefficient of performance for both the refrigerator and heat pump. Both are defined as desired output divided by required input. So for both the refrigerator and heat pump, the required input is the same, which is the work done by the compressor. But the desired output for a refrigerator is the cooling effect, and the desired output for a heat pump is the heating effect. So they will differ in terms of your COP definition for both refrigerator and heat pump in terms of QL and QH for both the refrigerator and heat pump. So you need to know the formula for both the refrigerator and heat pump, and it is defined as this. Now based on this, these relations can also be expressed in the rate form by replacing the quantities QL, QH and W net by Q dot L, Q dot H and W dot net in respectively. This relation implies, so this relation here, the last relation that you have got, COP-HP equals to COP-R plus 1, that COP for heat pump can be more than 1 since COP for refrigerant is a positive quantity. That is, heat pump functions at worst as a resistance heater, supplying as much energy to the house as it consumes. In reality, part of the QH is lost to the outside air through piping and other devices, and COP for heat pump may drop below unity when the outside air temperature is too low. So when this happens, the system normally switches to the fuel powered by natural gas, propane or oil, or resistance heating mode. Now, the cooling capacity of a refrigeration system, that is, the rate of heat removal from the refrigerated space, is often expressed in terms of tons of refrigeration. Now, for an example, 1 ton of refrigeration is equivalent to 211 kilojoule per minute or 200 BTU per minute. So a typical house with an area of 200 meters squared, you will have a cooling capacity load of almost 3 ton, and that translates to about 10 kilowatt, and you can use this value to design the refrigeration system that you need for the air conditioning purposes, which we will cover in the next. Now let's go on to our next part, which is the cycle. So the cycle that is used to define refrigeration is called refrigeration cycle, and we use working fluid. In a refrigeration cycle you need a working fluid. For your KJM 442 we will be focusing only on R134A. So this is the refrigerant that we use to operate our cycle, the refrigeration cycle that we have. And again, as you can see here, this is the refrigeration cycle that you have. So from the evaporator it goes into compressor, compressed, and then it goes into a condenser. Then you have expansion valve, and the cycle repeats again and again. So you need a refrigerant in this cycle. So same thing happens in the what do you call it, heat pump. So you can use the same refrigerant or a different refrigerant. So there are various refrigerants, right? But before we go into that, we have two parameters that we need to cover. So one is the QL here, as you can see here, and then another one is the QH. So QL is nothing but the magnitude of heat removed from refrigerated space at temperature TL. So this is the heat removed from the refrigerated space at temperature TL. Right? And QH is nothing but the heat rejected to the warm space at temperature TH. So please bear in mind, it's very important for you to know these parameters. Now this table here gives you some of the refrigerants that are quite common used in a refrigeration system. So they are actually denoted by the letter R, which tells you that this is a refrigerant, and they have a series of number after the letter R. And based on the series of number that you have, then it can be either in a methane series, ethane series, and so on. And you can also have its safety category and the glide category as well. There are many types of refrigerant. As you can see in this diagram, the table gives you the refrigerant that are mainly based on CFC. So as you remember, CFC is your chlorofluorocarbon based refrigerants. These are very dangerous refrigerants because if your refrigerator or air conditioning system leaks, this refrigerant can thin the ozone layer, and as a result it will allow more UV rays to come into our planet, and for human beings UV rays are very dangerous. So these refrigerants was used initially in our refrigerators, but in most countries they are banned now because they destroy the ozone layer of our planet, and they have been replaced by much more environmental friendly refrigerants. So to select refrigerant, there are two important parameters that you should pay attention to. One is the temperature of the refrigerated space. So when the refrigerant actually expands in the expansion valve, the temperature of as a result of that expansion must be at least 10 degrees lower than the required temperature of the refrigerated space. And the other criteria is that the refrigerant that we use must be environmental friendly. It cannot be destroying the environment in case of if there are any leaks from the refrigeration system. We have R134A, which will be discussing this extensively in our chapter here. It has replaced R12, which I've told you earlier that these are chlorofluorocarbon based. It damages ozone layer, and they are mainly used in domestic refrigerators as well as automotive air conditioners. R502, which is a blend of these two refrigerants, they are mainly used in the commercial refrigeration systems such as those in supermarkets, all right, shopping malls, all right, in factories, and so on. Now, as you can see in this table, the COP comparison between different refrigerants under same operating conditions, we notice that the ammonia has got a highest COP, but we can't use ammonia as in our domestic application because ammonia is very toxic. In case of any leakage, this can cause a lot of harm to human beings. So, but the industries, if they can place this refrigerant or the refrigeration cycle outside of their premises, then ammonia is the preferred refrigerant to be used for their refrigeration system because it has got the highest COP. This is followed by propane, butane, chlorodifluoromethane, tetrafluoroethane, and so on, right up to carbon dioxide, which has got a COP of almost 2.96. Now we will move on into the reversed Carnot cycle of the refrigeration system. As I have explained to you, our refrigeration system operates between two temperature range, which is the TL and also TH. So TL is the lower temperature, TH is the higher temperature range. So this reverse Carnot cycle, it is not suitable model for refrigeration cycle. Later I will show you what are the processes, right? So let's go into the refrigeration cycle as shown in this diagram here. And you have the TS diagram. So the reverse Carnot cycle is sketched here. As you can see, process 1, 2 is nothing but the process that is going where the refrigerant is going through the evaporator, and as the refrigerant goes through the evaporator, it absorbs heat from the cold medium, right? So that is the process 1, 2 represented on the Carnot diagram here. So this heat is absorbed, then from process 2, 3 it goes through a compressor isentropically, and then it reaches to point 3 here. Then from point 3 to point 4 it goes through a condenser, and in this condenser it is where you reject heat to the warm medium at TH, and then it is back to point 1 through a turbine here. So we use turbine to represent our reverse Carnot cycle, and this is done isentropically again, straight line down, and then that completes the entire cycle, one cycle of the refrigeration system, and you can continuously do this to reach the desired cold medium refrigerated space that you want. Now this reverse Carnot cycle in actual practice is not suitable because your process 2, 3 and 4, 1 occurs in the liquid vapor mixture zone. Now if you have your compression from point 2 to 3 which occurs in the liquid, we have the what do you call that, the dome, and then under the dome, as you can see, we have a mixture of vapor and liquid. If you deliver this mixture of vapor and liquid into the compressor, the process from 2 to 3 will not be practical, and this is because the compressor will need to handle two phases. And process 4.1 also involves a mixture of liquid and vapor, and this expansion of high moisture content refrigerant in a turbine is also not desirable. So we will see how we can modify the reverse Carnot cycle in our next slide, but I would like to bring your attention to the coefficient of performance. How to calculate the coefficient of performance for reverse Carnot cycle for a refrigeration cycle. This is given as 1 over TH over TL minus 1, and for a heat pump you have a formula which is slightly different than that. You have to memorize this formula because this is the COP is something that we will need to find for every refrigeration or heat pump cycle, and you can see that this is given by TH over TL. Now TH is the temperature at this region, TL is the temperature at this region, and both the temperatures must be in Kelvin. If you use degree Celsius, then you will get a wrong value for COP. Now both COPs increase as the difference between the two temperatures decrease, that is as TL rises TH will fall. Right, so this is another important thing that you need to remember. Now let's look at the ideal vapor compression refrigeration cycle. So earlier we were doing the uh, reverse Carnot cycle. This is the ideal vapor compression refrigeration cycle. So for an ideal vapor compression refrigeration cycle, you will see that all the components are same except for the expansion valve. In our Carnot refrigeration cycle, we had a turbine here. Now we have replaced the turbine with an expansion valve. Why we do that, we will discuss that in a while. Right? So the reverse Carnot cycle, why we call it a reverse Carnot cycle is because if you look at the direction on the TS diagram, it is a counterclockwise, right? So here we are doing ideal vapor compression refrigeration cycle. As I've explained to you, we have replaced the turbine in the ideal reverse Carnot cycle to our ideal vapor compression refrigeration cycle. Here we have changed the turbine into expansion valve, right? So these are the processes, right? Unlike the reverse Carnot cycle, the refrigerant is vaporized completely before it is compressed and the turbine is replaced with a throttling valve. So these are the two important differences between the ideal vapor compression refrigeration cycle and the reverse Carnot cycle. So process 1, 2. So now we want to draw the TS diagram. So this is how the TS diagram will look like. As you will see that you don't have a square anymore under the dome. So what we have done is, as I've mentioned earlier, we don't want two-phase vapor here. That means we don't want a mixture of liquid and vapor here. We want only a single phase vapor here. So you've extended the point number 1 in the Carnot cycle to the edge of the dome here. So once you reach here, your vapor is saturated. So now this is then sent into the compressor. So you have isentropic compression in a compressor for process 1, 2. And at point 2, from saturated vapor at point 1, point 2 becomes a superheated vapor region. So this is very important as we will be using this for our calculations later on. Remember at point 1 here, it is at saturated vapor. This is at superheated vapor. Then from point 2 to 3, point 2 to 3 in the condenser here, we have constant pressure heat rejection in a condenser. So this is then you reject the heat. As you reject the heat, the temperature drops from this point to this point, and this is done all at constant pressure. So this will then go from a superheated region right up to the saturated liquid region. And then from 3 to 4, we have the throttling in an expansion device. So this throttling, instead of going isentropically in a turbine, because we are using an expansion valve, it will be deviating in this manner. So this will go from 3 to 4, and then from 4 to 1 you have the evaporator region again, where you have constant pressure heat absorption in an evaporator. So basically these are the 4 processes that you can find in an ideal vapor compression refrigeration cycle. So this is the most widely used cycle for refrigerators, air conditioning systems, and also heat pumps. So we don't use the Carnot. Carnot is only for the reverse Carnot cycle is only for the theoretical, but we will use this ideal vapor compression refrigeration cycle. Now again, come back to the ideal vapor compression refrigeration cycle. So this is how it's represented schematically. In actual practice, this is how it's represented. If you have your fridge at home, at the back of the fridge at the bottom you will see a compressor. So this compressor, right, will send the compressed liquid through the condenser coil, which are also located at the back of your refrigerator. Once it has rejected heat, then it will go through the capillary tube or the expansion valve, and then after that it will go through the evaporator coils that are located at the top of your refrigerator, very near to your freezer compartment. This way you can then maintain the temperature in the freezer compartment at a very low temperature, which is -18. And we know these temperatures are very important if you want to preserve the food or prolong the shelf life of your food product. So you have four components. The first one is compressor. And what is the function of the compressor? Compressor is there to provide the driving force for the entire system by drawing low pressure refrigerant from here in and adding pressure such that it exits at high temperature. So that is the use of a compressor. Now condenser is nothing but you exhaust the heat out of the system. Alright, so you'll have a temperature gradient because the temperature here is high, temperature of the warm environment is low, so you can then have heat transfer taking place from the hot region to the cold region. Then you have expansion valve. It allows the refrigerant to expand dramatically in a control process such that it exits the valve at low quality liquid vapor mixture. And finally you have the evaporator to absorb heat from the cold space by virtue of temperature gradient, because you have this expansion. So this expansion allows you to absorb the heat from the cold refrigerated space. And this is again, as I've shown you, the refrigeration machine at home. So this is where the heat is being absorbed and this is where the heat is being rejected. So some formulas that we need to understand, right, before we move in further. Now we have discussed about ideal vapor compression refrigeration cycle. We have also discussed about the reverse Carnot cycle. I would like to point out here that the reverse Carnot cycle is the most efficient refrigeration cycle, operating between two specified temperature levels. So it is only natural to look at it first as a prospective ideal cycle for refrigerators and heat pumps. All right. The two isothermal heat transfer processes are not difficult to achieve in practice, since maintaining a constant pressure automatically fixes the temperature of two-phase mixture at the saturation point. So this and this is not a problem. Now why we change to ideal? Again, as I've mentioned, we need the compressor to have only a single phase. And why we replace the turbine? Imagine if this is your fridge and you have a turbine located here, it is going to be very costly and it is going to be a very complex design. So although if you look at the diagram here on the TS diagram, the cooling capacity is given by the area under the graph here. If you have a turbine, so the process, instead of going from here to here, the turbine process will go from 3 to 4 prime here, which will give you the added cooling capacity here. Now this added cooling capacity will definitely increase your COP, but having a turbine in a refrigerator instead of what you call that expansion valve will increase your cost and complexity of the system, right? So replacing the expansion valve by a turbine is not practical, right? It's not practical since the added benefits of this cooling capacity here cannot justify the added cost and complexity. So as a result of that, we will not use turbine here. We will still maintain capillary tube or expansion valve, right? So these are the steady flow energy balance equations that we will be using in our practice later on. And the COP for a refrigerator is given by this formula. COP for a heat pump is given by this formula. And you can actually calculate out your COP based on the enthalpy values. All right, for QL, you can calculate out the difference in enthalpy between 0.1 and 0.4, and the work net in into the compressor, the difference in enthalpy between 0.2 and 0.1. And for a COP for a heat pump, the definition is slightly different. So you need to calculate for your QH. For QH, the difference in enthalpy between 0.2 and 0.3, and W net in is similar to 0.2 and 0.1, the difference between enthalpies of 0.2 and 0.1. Now bear in mind H1, which is located at the edge of the dome line here, is at saturated vapor region. So you have to find Hg at this pressure P1. And if you look at your H3, H3 here is at liquid, saturated liquid region. So you have to find H4. So we will then do some exercises, but bear in mind, this is the norm that we use when we calculate our, or when we find our values for enthalpy at point H1 and point H3. Now what about H2? H1 is saturated vapor, H3 is saturated liquid. What about point 2? Point 2 is superheated, right? So we will look in the table later on what is the superheated region. Now this is a TS diagram. You should be able to draw this TS diagram out based on the information given to you in the question. You can also represent ideal vapor compression refrigeration cycle using a pH diagram. So you can see here pH diagram. Again, you have a similar dome which is different than this. Process 1, 2, where the work is uh, required by the compressor as shown here, and then press point 2 to 4 at constant pressure where heat is rejected, and point 3 to 4 again at constant enthalpy, and then process 4.1 where heat absorption takes place at constant pressure again. So most of the time in our practice we will emphasize a lot on our TS diagram, but bear in mind that we also have pH diagrams that you can use to solve problems related to ideal vapor compression refrigeration cycle. Now these are some of the formulas that you can use. So based on our first law results for compressor, if you want to calculate out the work in, right, based on the mass flow rate, is given by mass flow rate times the difference of enthalpy between point 2 and point 1. In the condenser, QH is given by mass flow rate times the difference of enthalpies between point 2 and point 3. Expansion valve, bear in mind that we assume our enthalpy at point 3 is almost similar to enthalpy at point 4. And evaporator, you are given QL equals to M dot H1 minus H4. And then these are the COP values. So you have to memorize the COP values for refrigerator, COP values for a heat pump based on this definition and also based on this definition. And this is for heat pump. You will see that they are slightly different. This is for L, this is for H. And then you will see that W in for both the compressors, you will have the same difference in enthalpy, but for heat pump, the difference in enthalpies are between H2 minus H3. Here is H1 minus H4. So you need to memorize this because you'll be using this a lot in your practices later on. And then based on the first law, we have these are the equations that you need to know for your compressor. These are the equations that you need to know for your condenser. This is the relationship between H3 and H4 for expansion valve, and then this is the QL relation for your evaporator region. Now let's look at our problem here. So we have a problem based on ideal vapor compression refrigeration cycle. So what you have here is a refrigerator uses refrigerant 134A as the working fluid and operates on an ideal vapor compression refrigeration cycle between two pressure limits, which are 0.14 megapascal and 0.8 megapascal. If the mass flow rate of the refrigerant is 0.05 kilogram per second, you are asked to determine these four parameters: rate of heat removal, which is QL, power input W in, rate of heat rejection to the environment, which is your QH, and the COP of the refrigerator. Now, your ability to draw this TS diagram will be tested again and again. So most of the time you will be given this problem statement. You should be able to at least sketch out this TS diagram based on this information given. So in this problem, the TS diagram is given. So we know that this is an ideal vapor compression refrigeration cycle, and these are the points that are of interest to us. This is where the heat is absorbed, this is where the compressor work is coming in, and this is where the heat is rejected, and this is the point of saturated liquid, and this is the point of saturated vapor. And the expansion valve direction goes from here to here, and we know the enthalpy at point 3 and point 4 can be approximated to be same. So now this is the skeleton that I'm going to provide to you, but you will need to fill in all the empty blanks here. All right. Now we have 4 points, point 1, point 2, point 3, and point 4. At point 1, we need to find what is the enthalpy. So to do that, we need to know what is the pressure. So the question tells you the pressure at point 1 is 0.14 megapascal. Now you need to know whether this is a saturated vapor, superheated, or saturated liquid. We have discussed this, that at point 1 the condition is that this is a saturated vapor region. So we go to table A12, we find saturated refrigerant 134A. Since pressure is given to us, we will use the pressure table. Now look at the pressure. Our pressure given to us is 0.14 megapascal. So if it's 0.14 megapascal, so we look for the pressure. 0.14 megapascal is nothing but your 140 kilopascal. And then we extrapolate here. We go and look for our enthalpy. So now enthalpy, you have saturated liquid and saturated vapor, right? So here we have saturated vapor. So we will go to the section of saturated vapor. So at 140, the value for saturated vapor is 239.16. And then that will be the value here, 239.16. Now if you look at it, temperature versus entropy. So you can also find the entropy at point 1. So entropy at point 1 is given here. So again 140 kilopascal, which translates to 0.14 megapascal. We go and find our entropy at saturated vapor, so which will give us a value of 0.94456. So you can jot it down here. Then we move on to point number 2. Now point number 2 is at superheated region. So the moment it goes into superheated region, you can't use this table anymore. Then you will need to go and look for superheated refrigerated R134A table. So this is basically a table A13. I've shared this table with you all. So please learn how to use this table. So now we will look at the pressure given to us, 0.8 megapascal. So we go to 0.8 megapascal. So this is the 0.8 megapascal. So now how to find the H2 is, you remember we have found the entropy value at point 1. And you know at point 1 this is going as a straight line. So when it is going as a straight line, we know that the entropy at point 2 is also same. So we can say here S2 is equals to S1. So with these two values, so you can see here we have entropy. So our entropy here, which we found earlier, is 0.94456. So you see that 0.94456 is between 0.9183 and 0.9480. So you will need to do some interpolation in order to get your enthalpy value here, which is your H value corresponds to your H2 value. So do that, and that will give you your H2 value here with some simple interpolation. Then we go to point 3. Point 3 is saturated liquid again. So this is at 0.8 megapascal. So we go back to this table because it's saturated, but this is saturated liquid. So we go to 0.8 megapascal. Why 0.8 megapascal? It is nothing but 800 kilopascal. So based on this 800 kilopascal, we find what is our saturated refrigerant, but not Hg, it is Hf. So we come to this saturated liquid, we get the value 95.47. So that is your H3. Now H4 is almost approximated equal to H3, throttling. So the same value here, you can write it down as the value for H4. So once you've got H1, H2, H3 and H4, then you can use the formulas that are derived earlier, that I've shown you earlier based on the first law and the second law. You can find your QL because m dot is given. You can find your W in, right? You can find your QH. Now interesting thing here is QH has got two formulas. You can either find your QH based on m dot H2 minus H3, or you can also find QH based on the energy law, where it should be equal to your QL plus W in. So this is the conservation of energy, right? So that will give you the same answer. And this is the formula for your COP. Since we are using refrigerator, not heat pump, so we will use the COP for refrigerator. So that will give you your answer for COP. Please do try this question because it will test your ability on how to read this saturated refrigerant on R134A table. You will then know where to find your enthalpy for the saturated liquid and saturated vapor. Also the entropies, and how to know point 2 is superheated, and where to find the value of enthalpy for the superheated region for a given pressure. And if you are required to do some interpolation, learn how to do the interpolation in order to obtain the value for H2. So please try this question on your own. I'm kind enough to provide you with a skeleton. All you need to do is just to fill up this empty spaces here. All right. So do try this question on your own. Now what we have here is actual vapor compression refrigeration cycle. In an actual vapor compression refrigeration cycle, it differs from the ideal one. Now you will see that in our previous compression refrigeration cycle, the compression takes place isentropically, right? But in actual practice, this will not happen, mainly due to fluid friction, which causes some pressure drop, and also you will have heat transfer to or from the surrounding. So as a result of that, your compression process from 1 to 2 might deviate from the isentropic line here, right? So there will be some differences. You will have non-isentropic compression. So this is a non-isentropic compression as compared to isentropic compression here. So you will have superheated vapor at evaporator exit. That is true for both the isentropic and non-isentropic. And you can also have subcooled liquid at the condenser exit. So instead of being saturated liquid, this point might shift slightly out from the dome line here. So then it becomes the subcooled. And you can also have pressure drops in the condenser and evaporator to be similar in both the ideal and actual vapor compression refrigeration cycle. So there are only two differences here which are highlighted in pink. The other two are basically similar. And this can also be represented in your TS diagram here, which corresponds to your pH diagram here, right? And to find your isentropic efficiency, this is the formula that we'll be using, right? So H2S is basically your enthalpy, isentropic enthalpy. H2 is your actual enthalpy, right? So in order to find your isentropic compressor efficiency, so this is the formula that we'll be using. So this indicates how closely you are operating compared to the ideal vapor compression refrigeration cycle. Now we have next problem, which is our sample problem 6.2. In our sample problem 6.2, you have refrigerant 134A enters the compressor of a refrigerator as superheated vapor at 0.14 megapascal and negative 10 degrees Celsius at a rate of 0.05 kilogram per second and leaves at 0.8 megapascal and 50 degrees Celsius. So these are very important parameters. You can use this to construct your TS diagram. The refrigerant is cooled in the condenser to 26 degrees C and 0.72 megapascal and is throttled to 0.15 megapascal. Now, I would like to ask you, can you draw your TS diagram based on the information given here? You should be able to, right? So disregarding any heat transfer and pressure drop in the connecting lines between the components, you are asked to determine A, the rate of heat removal from the refrigerated space, the power input to the compressor, the isentropic efficiency of the compressor, and the COP of the refrigerator. Again, for this problem, I have provided you with some skeleton for the solution. All you need to do is fill in the blanks, all right? So make sure you complete it, all right? So this is your TS diagram. So as you can see, based on the equation, it is superheated. It is not at saturated vapor region. So point 1 is already at the superheated region, and these are the parameters given to you. And then this is not isentropic. This is an actual refrigeration cycle. So it deviates from your isentropic line. And these are the parameters you need for point number 2. So here you can see that point number 1 and point number 2 are at the superheated region. Then point number 3 is again not located at saturated liquid region. It is slightly subcooled. But because it is slightly subcooled, we can assume it to be at the saturated liquid region. And then this is throttled to 0.15 megapascal at point number 4. So to find H1, we know H1 is at superheated region. So based on the same table that I've discussed with you earlier in the previous example, you go to the superheated table for R134A. Based on these two parameters, you find what is your H1. Then you find another pressure for the same superheated table. Based on this pressure and this temperature, you find what is your H2. Please note that these two values are found in the superheated R134A table because they are both in the superheated region here. Then P3 and T3, it's here in the subcooled region. But as I've mentioned, we can approximate it or assume that it is on the saturated liquid region because it's not far off from the dome line here. So we say that it's approximately equals to your enthalpy, saturated liquid enthalpy at 26 degrees Celsius. So you can use that value. And then since it involves throttling, you can find H4 to be equal to your H3. So that will give you the values of H1, H2, H3 and H4, and all these values are needed to solve your question to get your QL, W in, and also your COP. So here you can find your isentropic efficiency of the compressor. So this is the formula that we've discussed earlier. You have all the values for H1 and H2. Now the question is how to find H2S. So H2S, as you can see, it's going straight up from point number 1. So if you find point number 1, at point number 1, you need to find what is your entropy. So this entropy at point number 1 is similar to the entropy at point number 2s. So based on this value and this pressure, you can then find what is the enthalpy at point 2s. So try, this is already given to you. You can check with the table and then find out what is your efficiency of the asymptotic efficiency of the compressor. So please do try these two sample problems because you need to build your skill on how to read the R134 table and also how to do the calculations in order to find the values for QL, W in, isentropic efficiency. You can also find what is your QH and most importantly what is your COP. Again, pay attention to the discussion here. Once you finish both the practices, examples given here, please pay attention to the discussion here. What will be the COP difference between this cycle and the previous example cycle? So you will see that they are different, and look at the discussion and think about what you mean by having a higher COP for the previous one, right? And then why the COP for this one decreases and what are the reasons for it, and so on and so on. So these are the practice problems, right? So this will be the end of our lesson today. So before I end, I would like to advise you to do these practice problems. We have a total of 5 practice problems, right? So the problems are given to you with the answers shown here. So you should try all these questions, right? It goes on from a simple question, and then as we move on, you have Carnot, reverse Carnot cycle, actual ideal compression refrigeration cycle, and actual refrigeration cycle. So you have a total of 5 questions. So please try all of them, right? So if you have any problem, we will discuss it in our next class, and that will be the Okay, so with that, this will be the end of our part 1 for chapter 4, refrigeration and air conditioning. So for our next presentation, we will then go into our part 2, which will be focusing on air conditioning. All right, so thank you.